In the previous lecture, we have discussed the time-independent perturbation theory. You have seen the two cases, the non-degenerate state of the system and the degenerate state. How we can apply the perturbation theory to solve the physical problem we have already discussed. Now we are going to start another variational method, another approximate method to solve the physical problems. And this method is actually called variational method. In fact, this method was proposed by two well-known scientists, Rayleigh and Ritz. So this method is also called a Ritz method. Okay. So first of all, we will see some of the introductory facts regarding this variational method. In fact, whenever we follow any other method to solve the same problem, definitely there will be some drawbacks, some shortcoming in the previous method, and that shortcoming is removed in the new method. So actually, in nutshell, you can say when the method of perturbation or perturbation theory is unable to solve a problem, then we follow another approximate method, and one of the appropriate approximate method to solve such problems is the variational method. So I have mentioned here in this introduction that there exist systems whose Hamiltonians are known, but they cannot be solved exactly or by a perturbative treatment. So there are so many systems where what will be the Hamiltonian of that system, but that Hamiltonian cannot be solved in exact manner and also not by theory of perturbation. When you talk about this, then it means you are going to say that there is no closely related Hamiltonian that can be solved exactly or approximately by the perturbation theory. So in this condition, definitely we will seek about any other approximate method to solve such problems. And actually, in that very condition, one of the most important approximation methods that is suitable for such problems is the variational method. And as I have told you earlier, that this method is also called Rayleigh-Ritz method. Okay. In fact, you have studied this variational principle or variational method in physics, particularly in classical mechanics, in optics, okay, and also in quantum mechanics. In fact, often it is seen that the basic dynamical equations of physics can be derived from the variational principle. You have studied in classical mechanics the derivation of the Lagrange equations of motion, which can actually be derived from the Hamilton's variational principle of least action, or you can say the Hamilton's variational principle. Similarly, when you talk about optics, then you can see that the Eigenfunctions equation in geometrical optics derives from Fermat's principle of least action of time. Okay. I have provided videos on the field theory, and in field theory you have seen, if you have watched my video, that the classical field equations are also derivable from the variational principle. Okay. So it is therefore not surprising that the basic equation of quantum mechanics, which is called Schrödinger equation, what is the basic equation of quantum mechanics? That is simply Schrödinger equation. So this basic equation of quantum mechanics, that is Schrödinger equation, also is equivalent to variational equation. Okay. So actually in this method here, particularly in quantum mechanics, we are going to see to solve the problems by approximate method using the variational principle applied to the Schrodinger equation. Okay. So I hope you have understand when this method is applied to solve the physical problems. Okay. In fact, when you talk about this variational principle, what is the basic theory of this principle? First of all, we will learn about the basic theory, and then we will also learn in the last of the lecture the 4 steps by which we can solve any problem using this variational method. But simply knowing the rules or the laws, you can't solve the problem. When you take a particular example, a particular problem, then you learn about it. So in this lecture, we will not talk about any application of this theory, only we will discuss the basic steps which can be followed to solve the problem. But after this lecture, I will provide you some videos on its applications. Then you will learn how we can apply this theory. Okay. In fact, whenever you talk about the variational principle, definitely in that condition we require a function which should be stationary with respect to the variation of its parameter. That is actually called the trial function. Definitely you have to think about, first of all, a suitable trial function for solving the problem in accordance with the nature of the system, and that trial function will depend on some parameter. Okay. As you have seen in case of Lagrange equation, this trial function is actually the action variable denoted by the symbol S. Okay. So what will be actually the quantity which will be taken under account for solving the problem by using the variational principle in quantum mechanics? Actually, if you are talking about the problem of quantum mechanics, definitely you have to see the case of Schrodinger equation. And for the Schrodinger equation, the function which will be taken under account, that is actually the expectation value of energy, which is E of psi. And this expectation value of energy E of psi for the state psi is defined like this. You can see this is actually the bra psi h hat get psi over the scalar product of psi with psi. Now, if you will apply the variational principle, then a variational operator denoted by the symbol delta will be applied on it. And in accordance with variational principle, the delta variation of this quantity E of psi must be equal to 0. Okay. Now, in fact, if you consider that this function psi is in fact orthonormal, in that condition, the value of this product in denominator will be equal to 1. And normally in quantum mechanical problem, we take the eigenfunction which is actually orthonormal. Okay. Now, if you consider that this kth psi depends on a parameter alpha, okay, then E of psi will also depend on alpha. Okay. And then using this equation 2, first of all, we will have to minimize the function E of psi. Okay. We will have to minimize it, E of psi, by varying alpha. And the minimum value of E of psi provides an upper limit approximation for the true energy of the system. Okay. In fact, the variational method is particularly useful for determining the ground state energy and its eigenstate without explicitly solving the Schrodinger equation. Its basic aim is to determine the ground state energy, although we can determine the few excited state energy too, but the basic aim is to determine the ground state energy. Okay. So this method is based on the fact that the expectation value E of the Hamiltonian is always larger than the exact energy E naught. Actually, this E naught denotes the ground state energy. So E, which is equal to this much, that should be greater or equal to E naught. Okay. So we simply say that the without solving the Schrodinger equation, we can determine the value of E. Okay. In fact, here the sign of equality will hold only when this ket psi is proportional to the true ground state ket psi naught. Only then this equality will hold. If the ket psi is not proportional to the true ground state ket psi naught, then this inequality will hold. Okay. And as I have told you, if psi is normalized, then this scalar product will be 1. And in that condition, the expectation value of energy E will be given by this. Okay. And you know, in integral notation, this quantity, that is the expectation value of E, is defined by this. This is integral psi star h hat psi d tau, and that should be greater or equal to E naught. Okay. Now, first of all, we are going to prove this fact. Okay. If your aim is to prove this fact that E, which is the expectation value of the Hamiltonian for the state psi, is greater or equal to E naught, how we can prove it? Actually, for proving this, we will expand the trial function ket psi in terms of the orthonormal set of eigenfunctions, this phi n of the Hamiltonian. When you say that this set of phi n, it means phi 1, phi 2, phi 3 and so on. These are actually the orthonormal set of eigenfunctions for the Hamiltonian. Then this ket psi can be written as a linear combination of these phi n. So you can write that this ket psi is equal to A1 times ket phi 1 plus A2 times ket phi 2 plus A3 times ket phi 3 and so on. And in brief, you can write by using the sign of summation that this ket psi is equal to summation over n an times ket phi n. Okay. Now this phi n will actually obey the Schrodinger equation, and so you can write the eigenvalue equation in this manner, that h hat operated on this ket phi n will give En times ket phi n. Here En, you know, this is the energy eigenvalue of this operator phi n for the eigenstate of the operator h hat for the eigenstate phi n. Okay. Now, as this method is applied only when E naught is greater or equal to En. Okay. And this will hold for the non-degenerate one-dimensional bond systems. So in this condition, if you will evaluate the value of this E, okay, which is defined like this, then you know when we will put the value of bra psi, that will be An star bra phi n. Okay. And h hat is at is, and for this ket psi n, from here you can write this much, that is ket psi n times An. Okay. And Again, the scalar product of psi with psi will be given like this on the basis of this equation 5. This will be an star times an times the scalar product of phi n with phi n. Okay. Now an star times an, this will be a square of the modulus of an. Okay. And you know that this h hat phi n, this is equal to en ket phi n. Okay. And so I have written here that this is en times a scalar product of phi n with phi n. Now you can see that this this will be actually, yes, en times ket phi n times, yes. So this E will be greater or equal to E naught times summation over n modulus of an square and divided by mod of an square. And these two will cancel out, and so this is simply equal to E naught. Okay. So this result actually proves this equation number 3, which I have mentioned here. This is proven here. Okay. So in this way we have proved that very important result. Now, as I have told you that how we can actually apply this method to solve the problem. For this we will have to basically follow 4 steps. If your aim is to calculate the ground state energy, then that can be calculated in 4 steps. But this method is also applicable for few excited states energy calculation, which we will learn when I will provide you the proper example. Okay. So in first step for solving the problem, we guess the trial function. Actually based on physical intuition, we make an educated guess for a trial function that takes into account all the physical properties of the ground state. For example, the properties like symmetries, number of nodes, smoothness, behavior at infinity, and so many other. Okay. Taking these properties under account, we think about a trial function. Okay. And that trial function will be different for the different problems. Okay. Actually, for the properties you are not sure about include in the trial function, that is actually called adjustable parameters. And if these stable adjustable parameters are alpha 1, alpha 2 and so on, then actually this ket psi naught will be actually a function of alpha 1, alpha 2 and so on. Okay. And in fact this will account for the various possibilities of these unknown properties. Okay. So what will be your first step? Our first step will be guessing a trial function. Okay. And also you have to think about the properties on which that trial function will depend. Okay. Now in second step, we calculate the energy, this E naught. Okay. And this yields an expression which depends on the parameter alpha 1, alpha 2, alpha 3 and so on. So this E naught, which is actually the expectation value of the Hamiltonian in the state psi naught. Okay. And so this is defined like this. This is just the expectation value of E naught. Okay. You can see. This is our second step. Now in third step, using the equation which you have mentioned here, you have to search for the minimum value of this function E naught alpha 1 alpha 2 and so on. Okay, so for this we have to minimize E of alpha 1 alpha 2 so on with respect to alpha 1 alpha 2 and so on. It means if you are now minimizing it with respect to alpha 1, then you have to, when you will differentiate this E naught with respect to alpha 1 partially. Why partially? Because you can see E naught is not a function of only alpha 1, but it is a function of alpha 1, alpha 2 and so on. Therefore, you have to take the partial derivative of E naught with respect to alpha 1. And you know, if E naught is minimum, then this partial derivative will be 0. In the similar manner, you have to take the partial derivative of E naught with respect to alpha 2, alpha 3 and so on. So here I have in general differentiated partially E naught with respect to alpha I, where I means 1, 2, 3 and so on. But in a proper problem, you have to find these partial derivatives for I equal to 1, I equal to 2, I equal to 3 and so on. So this is the value of E naught, you know, and you have to differentiate it with respect to alpha I, that is alpha 1, alpha 2, alpha 3 and so on, and and then you have to equate it 0. Actually, when you will equate it 0 and solve this equation, okay, then you will have different values of alpha for E equal to E naught. So for E equal to E naught, the value of alpha 1 will be denoted by the symbol alpha 1 0. For alpha 2 it will be alpha 2 0. So these values will be obtained, as I have mentioned here, that solving this equation 9 you will get alpha 1 0, alpha 2 0 and so on. Okay, actually these are the value of alpha, different alpha, which minimizes this E naught. Now after getting the values of alpha 1 0, alpha 2 0, alpha 3 0, all these values are substituted in this equation number 8, okay, for getting the value of E naught, which is actually the ground state energy. So in this way, by solving equation 9, we will get the value of different values of alpha for which the energy E naught is minimum, and after getting those values we will substitute those values of alpha in the previous equation, and then you will actually get the approximate value of the energy. Okay, actually the value E naught alpha of alpha 1 0, alpha 2 0 thus obtained provides the upper bound for the exact ground state energy E naught. It means what will be the maximum value of E naught, that will be actually obtained. Okay, the exact ground state eigenstate, that is kth phi naught, will then be approximated by the state this much. You can see that psi is equal to this much. So using this result you can find the value of the phi 1, phi 2, phi 3 and so on. Okay, so in this way actually we can obtain the solution for the ground state energy. But what about the energy of the excited states? In fact, the variational method can also be used to find the approximate values for the energy of the first few excited states. For example, to find the energy and eigenstate of the first excited state, that will approximate E1. E1 is the energy of first excited state, and kth phi 1. When you will actually approximate these two, you will get the approximate value of the energy eigenvalue and energy eigenstate for the first excited state. And for this, what will be the trial function? For this, the trial function will be kth psi 1. Okay, and this kate psi1 must be orthogonal with phi naught. Okay, so this product will be actually equal to 0. Okay, so in this way, following the same method as we have minimized here E naught, in this case you have to minimize E1. Okay, and again you will get the value of alpha 1 1, okay, comma alpha 2 1, and so on. And after getting these values, again you can find the value of the upper bound value of the first excited state energy. Okay. Similarly, if you are talking about the second excited state, again you have then to think about the energy eigenvalue E2 and the eigenfunction phi 2. Okay, and in a similar manner you can solve the problem. Okay, so this is the basic principle how we can apply this method for solving the problem. But as I have told you earlier, by knowing after knowing this fact, the different aspect of the problem is not clear. That will be clear only when we will take a proper example. So in our forthcoming lecture, we will see a very simple example of one-dimensional harmonic oscillator, and using the variational method, we will actually estimate the energy of the ground state and also the first excited state and the second excited state. Okay. Although for your examination purpose, the energy calculation for the ground state will be more important, because the prime aim of this variational method is for the estimation of ground state energy. Okay, thank you very much.